Today I want to speak with, really, I like it, is that start recording. Okay. So today we are going to see some fascinating topic called DBScan, which is all about clustering. Okay. Um, I hope you got enough of recommendation engine. Do you have any questions there before I go into the machine learning based clustering algorithm? See, what I taught you about earlier, the k-means algorithm as well as hierarchical clustering, the statisticians developed that. Okay. So now I'm going to talk to you about machine learning algorithms, machine learning cluster algorithms. Any questions about recommendation
Dr.
engine?
Sam? Yeah, Dr. Sam, maybe can you like very high level review of the recommendation engine?
Information.
Just a very 10,000-foot high level.
So how about I go through the same codes, or you want to go back to that
Just the theory.
theory? Oh, okay, okay.
Yeah.
So let's
And
go. Let's go to this particular
theory. Yeah.
small. Actually, it is a small file. I spent more time in the codes, isn't it? But anyway, maybe because that applying those things are more
Like
complicated.
how the steps are, what the steps are. I mean,
Yeah,
just the steps so that I can
yes,
connect the dots.
yes, yes. Yeah, also, you will do lab. You remember that too. Okay, so
Yeah.
I'm pretty sure you will be comfortable by the time you finish. But anyway, let's do this small calculation I did. Okay, basic calculations. Here is that one. Remember this one?
Yes.
This is the very basic, and that captures all the essential things what we are talking. So there are users, these are users, and these are the items. Okay, and we have
Maybe
data.
I'm sorry. Maybe I think I was like confused with the when we got to data wrangling, the data wrangling
Oh,
steps.
data wrangling step is yeah. So I know. So that is that I will have to show it through the codes. I will go through that. Okay.
Oh, okay.
I'll go through that also. Let me quickly review here. So these are the users and these are the items. So not every user has given input whether which product he
Mm-hmm.
likes. These are items or
Right.
not. Which products he likes or not. He won't have it. Okay. And in fact, I
Right.
told you because of the long tail distribution, and which is always true. Most of the things are not going to be given score here. Okay. And these
Yes.
question marks are not given scores.
Right.
So what we are talking about is and let's also on top of it, let's say I have a new user here, okay, and the new user, well, we don't have to say new user and one more user, right? Because we have some scores here, so we don't have a new user with a completely unseen product
Okay.
usage or anything.
Mm-hmm.
Okay, so let's call this as the additional new user. This is use7. Okay, so he has one, these scores here. The problem what we are trying to solve is now, what can we have the four products are here, I1, I2, I5, and I7, which he
Mm-hmm.
hasn't tried.
Right.
If we are given a chance to recommend him, what is the best product he would recommend, so that he will like it. Remember, being relevant is very important in a competitive behavior. Okay.
Yes.
In fact, competitive behavior is not a bad word. I used to think I know it's a bad word. No, because being he is very competitive. That
Yes.
doesn't mean that it's sometimes used negatively. But what we mean is being relevant, being useful, and putting the effort to being relevant. That's all. Okay. So being relevant is extremely powerful in winning the hearts of people. Okay. So even in business, that's what it is, right? So what
Mm-hmm.
is the product next to recommend for this guy? I have four possibilities. One is I1, I2, I5, and I7. That's the question we are answering. So what we do is that we find out who are all similar in terms of liking behavior of this user with the already existing data. Okay. And so similar liking means, so basically who is correlated this with the most here, right? Users. And that we calculate using what is called the cosine similarity.
Mm-hmm.
So you can use correlation, Pearson correlation also, but this is what the computer scientists use it, and
Okay.
so we will use it also. Okay, and in fact, I to mention that it is similar to correlation quotient because it's a covariance divided by standard deviation without
Yes.
adjusting the
Mm-hmm.
denominator. Okay,
Yes.
same thing. Otherwise, right? Uh,
Yes.
so. Uh, so we use the cosine similarity and calculate, whether U1 is the first user is the more similar to this user, U2 is the more similar, and so on. So we find out the most similar, the top most similar people are U1, U3, U4. Okay, and so I can use just the U4 and then try to recommend that. Okay, but that's not a good idea. In fact, always average is a better idea than taking one
Okay.
item.
One. Okay.
So you take a neighborhood of people who are very close to him.
Okay.
And we consider in this small example 3 people who are neighbor to this guy, okay, in terms of liking. And these are U1, U3, U4 in terms of most liking. And so we do take that person's the average of these 3 people and then put that score and then recommend highest product. So the average of U1, U3, this guy, okay, the average of this guy, U3, and U4. Okay, we take these people, okay, and then average it. And when I average their scores for each of the product, this is what the score I get.
Okay.
You can see that, but what we want to solve is I1, I2, I5, I7. Okay, out of that, what is the top 2 or 3? In this case, 3, this one, and I7. Okay, that's all we are saying. Very simple, isn't it?
Yes. Yes.
Okay, but as you said, data wrangling is a big deal. It is not just big deal for recommendation engine alone. Please note that. I mentioned this in yesterday's session also. There are 2 major things when you are doing data science projects. One is you have to understand the story of the data. Am I making sense on that one?
Yes.
Yes, sir.
It is about what is going on, why a particular problem is important to you, explain, what is going on in the dynamics of people, interactions, products and services. And products and services doesn't mean just, commercial products and services. It could be your medication. Okay. It could be your, religious services. Doesn't matter. They are services. So people in life, this is what matters. People, products and services, and all the seller and all the people who are connected in that. For example, the supply chain, physicians. In the case of healthcare, it's physicians. It's the insurance company, and how they interact. This is what all life is about, isn't it?
Yep. Right now we have a supply chain problem.
Supply chain problem, but I'm saying in general, the key things are people who are consumers. And again, consumers, I'm using it in a very polite sense. I'm not talking about consumerism and so on and so forth. Okay, we are all consumers. Okay, anything you take, we consume time, we consume effort, we put effort, or consume time, prioritize, and consume other people's time also. Eat, of course, consume books, products, services, right? So we are consumers.
Yes.
Consumers, producers, partners. Okay, and the products and services. Life is all about this. That's it. So the story should. I'm going back to the statement. What is the story we are talking about here? The data story. I am a gray-haired person. I can talk like that, look like a big guy. Oh, what is the story and so on. But we have to politely ask. Okay, so tell me what is going on. Why do it's like a doctor speaking to the patient. right? What is going on? So Tom, you're saying, you have a big problem. What is the problem? You have a big opportunity. What is the opportunity? Why data science? Can you just do some kind of a calculation in the computation and then go on? No, there are uncertainties there. Okay, so he will say, he may not explain all these things. See, this is where you have to be a great story listener. So you have to ask politely, what's the problem? Why the Western region is not doing well? Things like that. No, do we know additionally what are the data we have? What are things like that. You have to keep developing this kind of talent in terms of listening to the problem. That is the story.
You have to know how to ask questions, I guess.
Right, ask right questions, very polite questions, but always with a very strong intents to help solve the problem. Because people are coming to you to solve their problem. Okay, so the story about the problem and the data you have to hear first, and then they give you the data. There are many steps in between. Okay, I teach this in 498. Were you in 498 in my class, Nini?
I don't think so, sir.
Okay, 402 probably you were there in 402.
I think I was in 402.
Yeah. So I teach in 498 now. There are data stories about the problem, opportunities, and then it is getting translated into data, right? You get the data, and then in between there are steps. How do you negotiate about data? How do you get the right data? And then the data will always have problems. So you have to figure out how to do the quality check, go back and ask for the data. I have done in my projects many times. I will get the data again and again because the data quality problems. Okay, big organizations. I'm saying it's not small organization. Okay, huge organizations. So because that's how people live their life. They don't care. Database manager just dumps the data, then he says, "Okay, data is available." But is that data quality data? The data, even if the quality data is there, they may not be sending the quality data. For some reason, things can always fall apart, right? So that is the second part of it. How do you get the data, parse the data, wrangle with the data to bring it to calculations like this? If the data comes like this, it's great, right? If the data comes like this, you solve the problem immediately, right? It's a 10 minutes work, or maybe 10 hours work, or maybe 1 week work. But you will be surprised. Most of the struggle we all have is 80%, 75% of the time you'll be spending time on getting the right data, wrangle with the data to transform it to usable form. This is called usable form. Okay, and that's what you saw in my presentation yesterday. Quite a bit of wrangling I was going through, but it's okay. It's not bad. I was going through, but it's not bad. By the way, are you able to see my screen? For some reason, it's not that.
Yes, see the screen.
Yes, we can see.
Okay. So I did some work for you, but in terms of going through. Let me see. This is. I need to make it bigger. Okay, I can't see myself. I can't see myself. Okay. See, I usually see it in a big screen. Now I see it in small screen. Okay. So new recommendation. Okay. So this is what I was sharing this with you. Remember that at the end I showed you for the top 4 people, what are the 10 recommendations, right?
Yes.
Okay. So what I was trying to tell you is that there are 2 things going on here. First, I have to wrangle with the data to bring it to rating matrix. That's what your real rating matrix is, what you feed into the recommender lab. That's one part of the wrangling. The other part of it, it is not a wrangling, but I really, we send the data to R as a real rating matrix. Okay, but what is going on inside, right? With the outputs, with the objects and so on. That's what I was trying to do here. The various averages, normalization, all those things I was trying to do. Is that clear?
Yes, sir.
Okay. Nini, you asked that question. Okay, is that clear what I'm talking? And
Yes.
I'll walk you through one more time, quickly. Okay?
Yeah, I just need a 10,000-foot
Okay, that's
overview.
fine. That's fine. That's fine. No worries. No, I'm glad you asked. Nobody asked it. You asked. That's good. In fact, because if one thing you have to when you learn one thing you have to do. These are all I make absolute statements. You have to review things, especially next day. Next day review is very important because that's where you see. Oh my goodness, I don't know what happened yesterday. I forgot that. I forgot this. Something you are talking about. It is important to review because the brain rests and then it comes back and then you review it. Oh, okay, yes. You'll have to get that review also. That's I'm happy with. And you guys should also ask. Rest of you should think like that. Do you get it? What I'm telling you, Anto, Kaushali, and
Yes.
Sharanya? I don't know if Sharanya is here. Sharanya is not here.
Yes, sir.
So review is very important. Even when you become a teacher, you have to say, okay, let's go recall what happened yesterday. You have to say that. I couldn't say it today because we don't have time. We have 15 hours of time, interactions, 15 hours of, this is a huge hours I give you, right? 30 hours I give you in a subject, but still it is so much for you to learn. Sometimes, I wish I can review, right? I always want to review because it's a good thing. It gives peace to the brain, right? Right, Nini? Nini knows what I'm saying.
Yes.
Okay.
Yes.
So here I'm just basically reading. I'm setting a set working directory. Is that clear? Nini, you asked good questions. So please, Anto, you should be like Nini and Gaushal, you too. You ask good questions. So, I want people to say yes or no, right? And Nini responds very well for me. Thanks a lot. Everybody should do it. So I set it up, the directory, and then read the data from that directory, movies and ratings. Okay. And I just do later on structure. All these things, I always have to take a look at the data, right? So there are four variables only: movie ID, title, genre. Genre is this kind of complex collection of attributes, different separated out by pipe symbol. I just translate the data into 0, 1, basically 0, 1 for each of these, basically. That's what wrangling is right now, right? So basically I did that, using this function tstr split, okay? String split from the data table. I get that, to split the data and so on. And then I convert it to data frame. So after I convert that, I basically also, I know the total of, these are the 18, different, different attributes are there, but yeah, movie is allowed only a maximum of 10. So that's why only 10 we do it here, but then total that the variations here in the genre will involve all these things. So I need to create a matrix of the number of movies times the number of genre type, and then I created a 0, and then I put one wherever these things come for each of the rows. Am I making sense?
Yes.
Yes, sir.
Excellent. So that's all. Up to this, it's done. Up to this is done. Now the matrix of zeros and ones based on the attribute, that is the genre, is available or not. Okay. And then because there are a couple of times the header is there. When you do the matrix multiplication, so on computation, you don't need the header. Headers are V1, V2, V3 like that. You can check it out, something like that. So we want to remove it. If not V1, V2, it is probably genre here, genre names. So we remove that also. Now it is pure data matrix because it's a data, as data frame we have this data, so we can do all the calculations. Then we also, because initially it is a character, we convert it to integer, okay? Things like that, that's all. So, and then we also, it is such a sparse matrix, we don't want to use it, and so we work with the sparse matrix concepts eventually. So all those things are coming. So this is what the data turned out to be. So this is, remember, it's a structure of a data frame is not, this is really a column. Okay, it is not row, it is really a column. There are
Oh, those are columns.
I'm sorry.
Oh, those are columns.
These are columns really because it
columns.
is
Okay.
it is the 18 genre type. This is
Okay.
9,125 rows and 18 columns.
Okay.
Right?
Okay.
18 is the genre types, right? So when you put structure, that's what you see. If you put if you don't put structure, but you use view to see, then you will know
Okay.
what I'm talking.
Okay.
Okay. When you put structure, variable comes in, like the columns are variable. They come in like this. So even before it happened like that. Look here. Even before
Okay.
movie
Yeah.
genre like that. Listen here. I'll go back. So when you do the structure here, movie genre 2, all those things. So structure here, movie genre, or structure here, movie data. That's what it is, right? Row by row. But here, 9,145 movies. Okay, 3 variables.
Okay.
Variables are like this. So these are the things you have to think very carefully, right? This should
Yes.
connect consistently with you, with your brain about data frames, data versus original data. This is what the wrangling is. And then there is a long form of rating. There are n number of n1 number of rating by first user, n2 number of rating by second user. These are rows. Then you have to convert them into a matrix of data. Like rows are raters, users, and columns are the movies, like that. So that structure you have to bring it in your brain. Very, very, very important. How the data is moved around, quantified, so that you can do your calculations. Either you can do your own calculation or you can use the packages. The rating matrix has to be set up in a way, then only it will take, the package will take. This you have to keep it in your brain. Not necessarily brain. You have to think about these things. But if you do few times, you know how to do it. Okay, don't worry about it.
Okay.
But what I'm saying is, you have to think about this thing. What form is that the data is given to us, and how we need to transform it? That is what the wrangling is about. How we need to transform it so that the package can use it, or you can do your own calculations. Very, very important thing what I'm talking. We don't spend enough of these things in real teaching. I don't know why, because they give you like this only, right? This I teach this is done.
Yeah.
Of course it is done, but in real life, this is not what you get. You get a bad data, messy data. You get very, data that the database manager gives you, and you cannot deal with them. They'll say, "Sir, this is what I get. You go and do your work." This is where the data engineer is supposed to be. See, for me, data engineer, he is not a pure technologist. Data engineer, he is still a these are things I differ with other people's opinions. Data engineer is basically preparing the data for you. Sometimes this can be a lot of work. Don't think it is easy.
Yes.
See, it's now written, so it is easy. That's why it's called wrangling. Somehow you have to make it work to make it workable for
Make
your
it
problem.
clean. Make it clean.
Clean it and also arrange it so that you can do the formula correctly to that. Or you can use the package correctly with that. That is what wrangling is about. It's not easy. Few things have to happen. You have to know beforehand what is that, the ingestion processes, data ingestion processes, or formula, calculation processes. And you have to turn the data to feed into that properly. That is wrangling. And in real life, you will face a lot of that. Because
Sir,
yeah. Go ahead.
Sir, I have a doubt.
Hmm.
Today I worked with some random forest examples and all. So in that they're given for a list of these packages and all. So how to find out which package will be good for the library packages will be suit for our data sets? How we have to find out all this?
Okay. Did you in a random forest? I teach you in
This carrot packages and all.
No.
Carrot.
There are many packages. You can use carrot package. You can use. There are a few other packages, but we teach you in machine learning, right? That topic. Can you wait until?
Yes, sir.
But caret
Yes,
is
sir.
good enough for you. Most of the time you can use caret. I want to use short answer. Okay.
Okay, sir.
All right.
Yes.
So I'm going back to this confirmation idea that Nini, the Anto, you guys understand what I'm talking about, data wrangling, why it is important. How do we transform the data that you get into a process that will computation, that will feed the computation formula or the packages directly. Okay, very, very important. Okay. So up to that, so I made up to this, right? The 001 up to this is very clear, and then
Yes.
I really do the most important final transformation. That is this one, decasting. That's what transforms the user rating, right? Rating data. It transforms the rating data into rows, remember, multi-line data for users, right? If I look at the user data, let's look at the user data, right? View, shows, rating data, sorry. So this is what your rating data is. Are you able to see this one, everybody?
Yes, sir.
And how many lines of ratings are given by the first user? Exact number.
25.
Take a look at it. The user ID is this. Movie ID is this.
So for user 1, there's 25.
20. Where is 25? 25.
25?
The user ID
No,
becomes
just
second 2. User ID
2.
becomes 2. User ID changes at 20.
20. Oh, we can. It's
20.
a little small.
Okay, I'm sorry about that. That's what I was asking. That you can see. Okay. So let me make it a little bit more. Okay.
Yeah,
So
better.
there are 20 ratings by user 1. And how many ratings by user 2? Can you figure out from these two numbers? Okay, it keeps going. How many ratings you
Already
get?
up to
96
96.
minus 20.
So 76.
76 ratings he has given the second user. But there's each line is a rating. We don't want this. This is not how you can use it directly into your formula or in the package recommender lab. It needs to be cast into each of the column is a movie. Just we need the rating, nothing else. Each of the column is a movie. Row is the user or the viewer or the consumer, the person who saw the movie and gave the rating, right? So we want to, here is the imagination you have to get. Remember, look at me very carefully and think about it, what I'm saying. I want to arrange each user and their ratings as columns for the movies. You get it?
yes, sir. Yeah.
Okay. That is what the decast is doing. The decast formula is doing that. Okay, that's what decast formula is doing. Do you see this one? I take the rating data, and then by using this type of arrange, this is the code we have to do, right? The rows are user IDs, columns are movie IDs. That's what this means. And the value variable is rating. Got it? Everybody get it?
Yes, sir.
So what do
Yes,
we?
sir.
So it's like you are transposing it.
Not really transposing. I am casting the data because if I transpose this, first of all, how many rows are there, you think, the rating data? There's nearly 100,004 lines, isn't it? If you look at the dimension of rating data. So I'm not doing a transpose. If I do the transpose, it will be 4 by 100,004 columns. 4 rows by 100,000 columns. Am I correct? We are not talking about that. We are what is called the long form data. This is also sometimes called long form data, right? This one. It is cast in a way, users are rows, columns are movies, and the points are the rated values. Do you get it?
Yes, sir.
Nini?
Yes, sir.
I'm still thinking.
Think, but let's try to view it also. Okay, we'll
Okay.
see. So we cast the data like that. This formula is beautiful formula, very simple formula. Okay, and then we make it as a matrix, and then we can view it, rating matrix. Hopefully
Okay.
we can view it, because if I have feeling, well, we'll have to see. Okay, yeah, up to this it is rating matrix, you can view it, but once it
Yes.
becomes like this, then you won't be able to view it. Okay, so let me redo this one. Okay, just for up to this one. Okay, I'm not worried. Now it is a matrix, so I should be able to view it. Let's see. Correct? Rating matrix. Super. Let's see. It's because it's huge. You see this one? Beautiful. Am I making sense? This is the movie ID. This is the user ID. This is the
Okay.
movie IDs. But most of them are NAs. That's what I was telling you. It's a sparse data. And the first movie, first user, I don't know where he is coming. Let's keep going. First user, okay.
There's
Movie 31.
2.5. Mm-hmm.
Movie 31.
Mm.
Who is this webinar registrant? We cannot take today. We are not giving a webinar. 1 second. Hello, sir, or Mr. or whoever that person is. Can you please? We are running a class now. So another time you can join. Okay. Sorry, I had to bounce you out. We are running a class now. I don't know what is it. Where did what is the purpose of your coming in? You thought today is exposure date? I don't know. Okay, I'm going to bounce that person. Mute webinar registrant. So anyway, maybe you can take it for a half an hour. Maybe you can listen how we teach. So this is the Nini. This is what it is, right? These are the
Yes,
register.
sir.
So he has given the score for the 31st movie. That's what this means. Until then, he
Okay.
didn't have any score, right? What is the next score? I think it goes after 1,000. We don't have here.
Yeah.
For limitation purposes, it will not show everything when you are
Right.
viewing data.
Right.
But
Okay.
let's take the second registrant, second user, right? So he rated 4 for the movie ID 10.
10. Mm-hmm.
That's what this means. And then he rated 5 for movie ID 17. Okay.
Yes.
All right. So like that you can interpret. But main point is, this is now, it was 100,004 rows before. But how many rows are now there, you think? We can find out that. Very easy. Dimension, rating matrix. It is only 671 rows and 9,066 movie columns. Are you able to imagine now?
Yes.
Super.
So we only have, that means that we're taking a look at only 671 users.
Even with the previous data also only 671 users here, right? The number of users are only 671 users, but these are all expanded version of the same data, right? Because there are, each rating is given 1 row of eligibility to have its data. But now when we do the decasting, it comes out to be like this. It's beautiful because this is the kind of thing you use it for for computations purposes, not this data. So this is the wrangling part, that you move the data into this part. This is 100,004 rows and 4 columns. We dropped this, for example, movie IDs are not needed. Okay. Movie IDs become, actually, I'm sorry, not needed. No, it becomes a columns. Really. Columns. We don't need the timestamp. We put this as the value in the matrix. Okay, and this is the rows, this is the column, this is the values. That is what happened in the decast.
Okay.
Okay, that made this possibility, rating matrix. And now, of course, this is still a lot of missing values. This is in a what is called the sparse matrix form. You don't need to store these things, because there are only, how many valuable values are there. There is something like, wherever it is filled up, right, and which is hardly 20% or 10%. Okay, so the remaining 90% you don't have to waste it. There is a sparse matrix notation helps you to eliminate, the space usage, and keep the calculation still valid. That's the beauty of the sparse matrix. Okay, and that is done. Once that is done, I convert it into, again, the last part of the wrangling is that right now it is viewable by us as human, right? But then we make it into an object that is, used directly into the recommender lab. That is what is this next step is. That is, I'm saying, I'm going to, convert it into an object called real rating matrix.
Okay.
So, as rating matrix, this data and to real rating matrix, that is the terminology conversion process. There's something going on. The as function, as function will do something to this, and call it as real rating matrix, so that is usable directly into the recommender lab. That's what the point is. Okay? Up to that, so I converted that, and then I'm even checking it out. So let's just quickly do this one. And then now I'm checking it out, right? It will say something as S4 object. It was a matrix before, now it has become S4 object, relevant for, but it didn't say S4 object of the recommender lab, actually. Okay? Then once you have that, it knows, recommender lab, package knows how to deal with this rating matrix data to do all its calculations. And then the moment you put the recommendation model, this command, boom, it's over. It's done. It has done a lot of things actually, but I'm only going to access this. Okay, that is a specific collection of my entries that are created by that, and that's where the. So let me just run it one more time, and then it's not run. So there's some problem there. Okay, what is it? What's going on? Object not found. Okay, because I didn't do the recommended lab library. See, I didn't do the library. That's what's the reason. Okay, and I think somewhere I use this one, so I will take that. Also, alternatively, I could have done like this. Okay, so once that is done, it should work. It's okay. So what are the things it has got? It has got all these things in its basket. It has done all these things. So, and then after that, I show you some calculation. That's all. Similarity calculation. I just want to pick up a few things because it is. I can use the rating matrix even though it is a S4 object. I can use it, along with the function similarity functions. Okay, and I'm basically calculating similarity measures based on users. I can also do based on, and then I'm viewing it. Okay, that's all. And then I can also use based on items. Either way is okay. So there is item-based collaborative filtering, user-based collaborative filtering. I'm just viewing some of this data. I explain those things for you. And then I'm kind of just saying, okay, what are the unique values? How many, all those things, how many different unique values are there in the ratings, and then viewing some of those scoring and all those things. And then what are these are all just understanding more about the data. But the problem is already solved. Recommendation engine based solution is already created. I'm just showing some additional calculations here. That's all. Just to more and more familiarize about the data. Okay. You're done with this one, right? Just a quick review. Okay. So now let's go to webinar register. You have to introduce yourself. I'm happy to hear you out. It's okay. You can stay some more time. I need to know.
Kaushali, sir.
Huh?
Kaushali, sir.
Kaushali, okay. Miss Webinar Registrant, welcome. Okay. All right. I was about to bounce you, because I don't want unknown people, right? It's our private class. Okay. Now, are we ready to go to the clustering, DBScan, HDBScan optics?
Yes, sir.
Super. Okay, so let's do that.
Yeah,
Remember,
that was good. The review was good. Then I'm able to connect a little more.
yes, I'm telling you, the review is very, very important. No worries, okay? In fact, when you do, in fact, we are very lucky today to do the review, because yesterday we did it, we slept on it, and then we came back and reviewed, right? Sometimes when you do previous week and come back and do, people don't remember. It's very difficult. I understand that, because there are so many things happening in between the week, okay? There are things happen at home, there are things that happen at school or college or at office or in the community. You go to a store, something happens there. Go to a gas station, something happens, right? So we get
Yes.
distracted. Our brain is, loses some of those vibrations. So it is harder actually. But because yesterday it is fresh, and it is good to do that always. Okay. All right. So I want to tell you that now all clustering is about distance calculation. In fact, similarity and distance are same. Distance is a opposite of similarity. You need one of that. If you have similarity, you can calculate distance. If you have distance, you can get there is some kind of a conversion formula you can find depending upon the mathematical definition or distance you use. There are many distances you can use. Okay. Euclidean distance is the most common, which is the Pythagorean type distance. You know what I'm saying? In a rectangle, Pythagorean distance, the diagonal, right? That is the Euclidean distance. Okay. The cross entropy is also type of distance. Entropy is also type of distance. Okay. So it is important, broadly speaking, to think in those terms. Distance and similarity is the most fundamental thing in terms of finding, look-alike people, look-alike objects, animals, things like that. Okay? And we did see k-means, and it was an iterative procedure, right? K-means is an iterative procedure, but we will always get unique membership of each observation to each of the clusters. We also saw hierarchical clustering. Okay? Those are things we saw. And here is the comparison between graph representing identification of micro-classifications, noise detection, and efficiency. If you look at this one, K-means is very, very efficient, right? Efficiency, very, very efficient. It is also, compared to noise detection, and also in terms of the microclusters identifiability, K-means is not that great. Okay, but in terms of the other side, other extreme is DBScan. It takes time, but it's okay. It is it can identify microclusters, because I'll show you the example pretty soon. Okay, and nonetheless, efficiency is not that bad. It takes time, but efficiency is pretty good. Okay. So my point here is that now I want to introduce this DBScan and its class of clustering, which is very powerful in my opinion. And in fact, I'm very happy to teach that. You don't get to hear this in graduate school. Did you have a chance to learn that before?
DBScan, a little bit, sir. We touched on it a little bit.
Okay, DBScan, HDBScan, and also optics.
Not HDBScan, just DBScan.
Okay, fine. So, but here is the quick review again. I told you that Euclidean distance is very important. The distance between 2 points x1, y1, x2, y2 is this. This is Euclidean distance, square root of x2 minus x1 square plus y2 minus y1 square. And so this is the h1 vector. This is the h2 vector. Okay. So the distance between h1 vector and h2 vector is this one, and we don't need perpendicular angle here, 90 degrees to calculate distance. So if you have an angle less than 90 degrees, how do we calculate? Just use the cosine function. That's what this one is. This distance is equal to distance square is h1 square plus h2 square minus 2 times h1 h2 cosine phi or cosine phi. Okay, this is the phi, angle phi.
Okay.
So this is the, if you don't have 90 degrees, how do we calculate distance? This is what it is. Okay, so that's where the cosine function comes into play. And cosine similarity and its relationship to Pearson correlation is, again, I'm mentioning it here. Okay, so this is again, if you have a vector A and vector B, this, this is the measurement that you can get using this formula. Absolute A, that's a projection of A onto this B. Okay, absolute A times cosine theta. So this distance, this part, whatever I'm saying here, one more time I will show you. That distance, that part, right, is basically the absolute value of A, which means really the distance. Remember that it's a norm, okay, distance. Okay, the distance from 0, 0 to up to this point, x1, y1 times cosine theta. Okay, now we can use that to to basically talk about how to use angle theta in this case. How close it is to this form, to the vector B. So that's the kind of thinking we were earlier measuring. Cosine theta is measuring how close it is to the vector B. How close A is to vector B. So these are all some basic formulas by which we calculate, we get convinced that cosine theta is a good idea. Okay? And then this is a quick review of the k-mean clustering. We did that last time. And this is what I want to introduce today. It's called DBScan, that is density-based spatial cluster applications with noise. Okay, density-based spatial cluster applications with noise. And take a look at these points here. Okay, there is a point here, B. There is a point A here, noted. The rest of the points are not noted, but these are important points, so we noted C is here and N is here. Okay. And in DBScan, there are two things that defines the clusters: the epsilon and the minimum points. Epsilon defines the circle or the sphere. Okay, you can define any epsilon, that's fine. But once you keep that fixed, and you also have to demand, I want to construct an epsilon going around all over, and as they go around, that it should cover minimum points, number of points, in this case 4 points. So here is a circle I constructed with the epsilon unit. Let's say this is epsilon unit radius. Okay, I move around the I move around this page. When I move around the page, everywhere as I move around, when I center around that and move around it, it should contain minimum of 4 points. Then it is called interior points for the cluster. Okay, if it doesn't have any point other than the point itself, that is called noise. If it has any point, okay, with the condition that it should contain 4 points, then it is an interior point. But as I move away from that, it will contain at least 1 point, but not the minimum of points. Then it is the outer point. So if you put center around C, it is not just C alone. It has one more point. That is this point. Do you agree?
Yes.
So this is an outer point. It doesn't have 4 points, but it has 1 point, and in addition to itself. But if I come here, what is the circle? No, I have to probably put the circle and then move around. Then it's probably easier for you. So let me do that. Okay. Let me put this first. So as I move around, you see there are 4 points. Do you agree? This is centered around this, so 4 points. That is an interior point. Agreed?
Yes.
How about now I move to this point, next point. Does it have 4 points?
Yes.
Centered
Yes,
around
sir.
A. Centered around A, yes. So it's an interior
Yes.
point. How about this? More than 4 points. So
Yeah,
it's good. Okay, it's good. It's also interior points. Okay. How about this point? This is also more than, I think, more than 4 points. I mean, my circle is a little bit lower in size, smaller in size. Okay. And so that is also an interior point, right? Like that, we got to move around. Okay, check every point. How about this point? This is also an interior point because it has 4 points. It has, of course, the B point also inside, but it has 4 points. But how about this? I center around the yellow. It has 1 additional point.
that's 2
So
points.
it is an outer point, but it is not an interior point. Got it?
Yes, sir.
But what about
Got
now? This one, finally. There is no other point other than itself. So it's a nice point. So this methodology, very simple idea, beautiful methodology, because it can identify very unusual clustering point, geometrical clustering direction, clusters very nicely. Okay. And it has its own very interesting twist also to the story. I will come to that. But the point is, this is how it goes around. This very simple. Algorithm is very simple. Okay. So let us go here. I'm going to keep this one here. Let it keep. This is the minimum. This is the epsilon. Okay. It's the minimum point. I'll leave it like that. Next time I don't know. If I have points clustered like this will do the job very beautiful, very nicely. But there are problems with your k-means, hierarchical clustering, these kinds of things. You remember I showed you some example. These things will be difficult, right? Here it happens without much fuss. Doesn't matter. When you have large cluster and small clusters, it will create problem. Remember that I told you. Even though we have some tricks to do that, this naturally will solve the problem. All these things will be done very nicely, easily. You understand that, right? But these are all out noise. These are all noises. Because when you go, epsilon, remember it will be epsilon, very small epsilon that will do this, right? So if you go there, it will be separate points. But these things will work out. Agreed? So the DBScan is 0.2 units of the circle or sphere, and then 4 units. Minimum points is 4 units. That's what this solves. Okay. I have some notes here, video. So the thing is, no, it's not a video. It's not a video. Oh, well, it is. I see. Okay. Okay, that's fine. So the main point here is that DBScan is a density-based algorithm. I have a couple of small videos there, and the important point here is that the optics helps you to identify how many clusters are there. See, how many clusters is very important, right? Number of clusters, right? So in the case of DBScan, it goes with the optics. Optics is ordering points to identify clustering structures. Basically, how many clusters are there? More important, okay? Of course, it will also give you, which is a large cluster, which is a small cluster, all those things, but it doesn't matter. Number of clusters is very important because the geometry will tell you, when you plot the clusters like this, it will tell you how many clusters, which one is big and which one is smaller. So it is basically, you need to have a cut points defined by this is the epsilon axis, okay? This is the cluster order of the points. Some observations are closer to other observations and so on here, right? So this is the order of the points, I mean, this is the points here, and this is the epsilon here. The minimum, the radius of the sphere is here. So as you increase the radius, think about it. When you increase the radius, what will happen? You will have less number of clusters. As you decrease the epsilon, you will have more number of clusters. Am I correct?
Yes.
Good, excellent. Thank you very much, Mimi. That is what this graph will help you, and that graph is created by optics. Okay, and so here are some important things. Your DBScan will give you all these outputs. No worries. Okay, so we talked about how these points are can be identified, and then generalized density-based spatial clustering applications generalizes the notion of point densities, and it can be applied to arbitrary data type, and it's also the types. Sometimes you can use it in for lands, land identifications, land clustering in the geography and so on. Okay. And then I was telling you that now, if you look at this picture, it's small maybe. You can also identify, the inner clusters, more denser clusters inside another cluster and so on. So here, for example, the small things, number of things are there, the small points are there here. The spikes are the one that talks about, identifies you to the high density points, in the clusters that you are identifying, high density points in the cluster you are identifying. Okay, so that's what I wanted to share with you. But here is the code that I wanted to share. It's pretty straightforward, right? You agree with me on that one? And if you know it, yes, of course, that may be the point you might say. So I think the way I moved around the circle, it captures. This is another example you can move around and see. But these things will not belong to the clusters. Okay, this is the only point that will belong to the clusters, because we are talking about minimum 4 points. Whatever the unit of circle is 1 here. You can see here it is only 3 points, not 4 points. Again, these 3 points. So these are all, these are all outside. But the moment you go inside here, there are 4 points here, 4 points here, and so on. This is the noise point, nonetheless, and this is the border point. So really, the central points are this is the cluster points here. Okay. Of course, you can include the noise of the border also. That's okay. The border is also okay. But you do want to identify as border. But the thing is, you are really identifying the noise. These are the noise points here. Again, as another example. Okay. So here, another example I'm talking to you. Okay. In this collection of points, if epsilon is getting smaller with minimum points same, there are more clusters. Also, if minimum points are decreasing with the epsilon, same epsilon, then the cluster size increases. Okay, because we are expecting less number of points for the same epsilon. So cluster. So this is a question of when does the cluster size increases and decreases. Okay, when the epsilon is getting smaller with the minimum point same, there are more number of clusters. And if minimum points are decreasing with the same epsilon, then our cluster sizes increases. Okay. So here is a fascinating example. These kinds of geometric patterns is easily resolved by DBScan. Easily resolved. Okay. And it's very difficult, in other methods. So these geometric patterns also, means, for example, in fact, people haven't used it much, even to classify the health images, right? You can use DBScan. But health images or pictures, you can use DBScan. And remember, this is not a unsupervised algorithm. This is not a supervised algorithm. It's an unsupervised algorithm. Am I making sense? Yeah, everybody?
Yes, sir.
This is not a
Yes, sir.
Yes, sir.
not a supervised algorithm. It's unsupervised. Remember. So you get one more powerful supervised algorithm, one more powerful unsupervised algorithmic method to solve clustering problems, especially. Okay, same thing. And these are all beautifully identified as noises. Even here, this is identified as noise. Okay, by properly getting the epsilon. So that's why identifying epsilon is very, very important. But that you can do it only by the optics tool. You get it where I am connecting to the optics tool. Only optics will help you to do that, to find out what is the right epsilon, because that determines the number of clusters here. So then you still want to worry about when does the DBScan does not work well. If the densities are quickly changing among the points, then it may have problems. So these are the original points. Really, this is what we want to identify. These are the original points. But depending upon epsilon, these things might become the noise points. So in a particular example, in this particular paper, with the epsilon is equal to 9.92, mu 0.4, it identifies all these things. It identified this, but it did not identify this as a cluster, but it identified as a noise. So there are more examples like that. K-means versus DBScan, a little bit of notes here. The K-means, if you have, when K is equal to 3, you want to identify only 3 clusters, okay? And minimum points is 4. This will be considered, these 3 things will be identified correctly, okay? These 3 things will be identified correctly, but, this thing will be, this one will not be identified as any cluster, even though there are 3 points there. It's a cluster. It's a small number of points in the cluster. This will not be identified, right, by the DBScan, because we want 4 points. But this will be identified by the K-means as another cluster. If you ask, but because you are asking only for 3, do we say that? No, we don't say anything, right? So if you say 3, it will be identified these things. But you can get 4 or 5 also here in K-means, and it will work out okay. But then if you look at this one, okay, there are naturally 2 clusters here, and according to the DBScan, the K-means will identify it as K-means will identify it as this will be identified as 2 clusters by the DBScan clearly. Okay, if it is less than the epsilon is more than the distance between this, the average distance seems to be the same, right? But almost, right? So let's say this is 1 unit, right? The distance. Then something like let's say 1.2 units or 1.5 units. This will be identified as a 2 cluster by DBScan. But if you use the K-means, again it depends on the K-means. You ask for 2 clusters, it will probably it will identify these 2 clusters as something here. 1 cluster, depending upon if you said 2 clusters, it will identify this as 2 clusters. 1 cluster here and 1 cluster here in this range. Okay, some of these points will be left out, but because you want 2 clusters, yeah, some of these points will be left out. These boundary points will be left out. Am I making sense to you all?
Yes, sir.
Okay.
Yes, sir.
So you have to think, again, remember, next time when I review, it may look easier to you and so on. But then you have to think about all those things. So DBScan, so clusters found in random data. Sometimes, even in random data, DBScan will find clusters because it depends on the epsilon size, right? And the minimum points. So if you use this is the random point, if you use the DBScan, it may look like it's a cluster. It does look like a cluster, right? More dense points are here. Right, more dense points are here. That's what more dense points are here. More dense points are here. That's what the DBScan will do. Okay. But if you say k-means, I want k-means out of this, again, these things look like much closer, you get 3 clusters. There is no cluster here. That's a random point. Okay. And if you do the complete linkage, you can see there is one cluster here. And because of the linkage, this green is one cluster. These reds are all one cluster, and these blues are all another cluster. I don't know whether you can see the difference. This is one cluster by the complete linkage. This is k-means. This is a hierarchical complete linkage. There are 3 clusters if you want it. They will, these things will go together. These things will go together. This green will go together. So even in random points, it may look like you can find clusters based on the conditions you use. You just said 3 clusters. I wanted k-means. This is what it will find. If you say with a certain epsilon and a minimum points, it will find out 3 clusters like this. And in complete linkage, if you look for 3 clusters, this is what it will be. Because remember, number of clusters, you have to define the distance in the distance matrix, right? By moving at the right distance, you can find 3. If you are looking for 3 clusters, this is what will be the result of that. For right parameters in any data set, an algorithm will find clusters. So you have to be careful about this. That's my point. Okay. So that's a kind of quick review of, DBScan, and I need to give you some codes analysis. Let me see. You can take a break and come back, another 30 minutes, and I can show you the codes. Is that okay? 5 minutes or 10 minutes? Is that okay?
Yes, sir.
Everybody?
Yes, sir.
Yes, sir.
So
5 minutes.
I'll be showing this, this code when you come back. Take 5 minutes.
Sure.
Yes, sir. Thank you, sir.